Throughout Earth's long history, life has faced numerous challenges, but few events have been as catastrophic as mass extinctions. An extinction event is the name given to events in history during which a significant percentage of plant and animal species disappear in a geologically short time. Scientists tell us that there have been multiple extinction events in eons past, generally identifying what are called the Big Five mass extinctions. And none have captured our imagination quite like the one that ended the age of the dinosaurs. This, called the KT extinction event, occurred 66 million years ago, long before humans walked the Earth, but relatively recent in the scheme of things. To put this in perspective, 4.5 billion years ago, the Earth formed, and 3.5 billion years ago, the first life appeared. 230 million years ago, dinosaurs started to evolve, and 66 million years ago, the KT extinction event. Humans appeared only 300,000 years ago, and of course today you're watching this video. For over 160 million years, dinosaurs ruled the Earth. From the tiny velociraptor to the towering Brachiosaurus and the ferocious Tyrannosaurus rex, these magnificent creatures dominated every continent, evolving into a staggering array of species. But their reign was about to end, not with a whimper, but with a cosmic bang that would rewrite the history of life on this planet. Our story about the death of the dinosaurs begins in the recent past, near the picturesque town of Gubbio, Italy. Nestled in the Apennine Mountains, Gubbio is a place where history whispers from every stone. Founded by the Etruscans over 2,000 years ago, Gubbio boasts remnants of its Roman, medieval, and Renaissance periods. Its ancient streets and well-preserved buildings draw tourists from all around the world. In 1977, a young American geologist named Walter Alvarez came to Gubbio not for its architectural wonders, but for its rocks. Just outside the city walls lay a geologist's dream, one of the most extensive continuous limestone formations on the planet. These pink limestone outcrops, known locally as Scaglia Rossa, represent an ancient seabed spanning some 100 million years of Earth's history. These limestone rocks were formed by sedimentation, the settling of material floating in the ocean waters that sank to the bottom of the ocean, and over a long period of time became limestone. Hidden within these limestone rocks was a mystery that would challenge our understanding of Earth's past. Alvarez's objective was to investigate geomagnetic reversals of the Earth's magnetic field, which is recorded in these deep-sea limestones as part of working out the details of plate tectonics. Using this data, Alvarez and his colleagues would be able to date any magnetic reversals across a time interval of more than 100 million years of the Earth's history. One technique they used for studying such reversals is foraminifera biostratigraphy. Foraminifera, or forms for short, are fossilized shells of tiny sea creatures. These tiny organisms, among the first complex life on Earth, have been around for over 500 million years, and their fossils are a valuable tool for geologists in dating rock formations. However, as Alvarez studied these formations, he noticed something very peculiar. Throughout the limestone, as he expected, he found these fossilized shells of forms. But there was one layer of sedimentation within the limestone that was very puzzling. A thin layer of clay, just 1 centimeter thick, separated two limestone layers. Within this layer of clay, Alvarez found no fossils at all. Even more intriguing, he quickly recognized that the forms in the older rock layer below the clay layer were much more diverse and much larger than those forms found in the younger rock above the clay layer. This dramatic change in life forms was not gradual, it was abrupt. What did this mean? Alvarez realized that something had happened that dramatically destroyed the older varied population of forms and reduced the younger population and distribution of forms in an extremely brief period of time, geologically speaking. A few months or a year or so. This was earth-shakingly impossible based on what was then known about Earth's history. Alvarez had discovered what geologists now call the KT boundary, the dividing line between the Cretaceous period and the Paleogene period. This extinction marks a major boundary in Earth's history, also called the KT or Cretaceous Tertiary boundary. This clay layer defined the end of the Mesozoic era, the 180 million year era of dinosaurs. This boundary marks one of the most significant extinctions in history, the end of the age of dinosaurs. In any case, the accepted common knowledge was that this extinction should have taken millions of years. However, the thinness of Alvarez's clay layer indicated just a few years at most. Impossible. Until recently, people simply knew that dinosaurs went extinct. Their fossils were found throughout the Mesozoic era, but there were no dinosaur fossils found in the rock layers or strata of the younger Cenozoic era. That's the current age, 66 million years ago to the present. So, paleontologists knew that dinosaurs went extinct some 66 million years ago, but no one knew why. Many scientific hypotheses had circulated for decades about how the dinosaurs were rendered extinct, but they were just hypotheses and guesses with no supporting evidence or data. Proposed theories included that dinosaur extinction occurred because mammals ate dinosaur eggs, or dinosaurs overpopulated and ate themselves out of food, or there was a rapid climate change due to volcanic activity. One suggestion was that the dinosaurs simply reached a natural end of their lifespan as a species. Others modified that suggestion to suggesting that their life science simply made them unable to adapt to environmental changes. If that was the problem, then why did not the many smaller dinosaurs survive? There were a lot of suggestions, some firmly held, but no data, no proof. Alvarez needed to figure out what caused this sudden change in the forams population before and after the time of the clay layer. How quickly did the clay layer of sediments happen? Did it happen just in the Gubbio region or anywhere else in the world? And what did it mean for life on Earth? The location of the weird layer within the sedimentary layer of limestone placed its time of formation about 66 million years ago. But he needed to get a much more precise reading on the date and of course the possible causes for formation of that weird layer. Did the layer potentially provide information about some event affecting life on the planet when the layer was formed? To tackle these questions, Walter turned to a readily accessible but unlikely collaborator, his father, Luis Alvarez. Luis Alvarez was not a geologist, but rather a Nobel Prize-winning physicist whose specialty was nuclear physics. His Nobel Prize in Physics was awarded for his groundbreaking work in subatomic particles. Walter's dad was a scientific powerhouse. He was one of the scientists selected by Oppenheimer to work on the Manhattan Project during World War II. He would also be awarded the Collier Trophy for his development of a ground-controlled approach system for aircraft landings in bad weather. Now in his late 60s, Luis was intrigued by his son's geological puzzle. Walter needed a way to, as accurately as possible, date the time of occurrence of the clay layer he had found in Gubbio, and to determine if that layer existed only at Gubbio, or was it also found elsewhere on Earth. Together they began brainstorming ways to measure the rate of change around the KT boundary. Luis, with his deep knowledge and experience of particle physics, was of course the ideal partner for Walter for the brainstorming sessions. He remembered that meteorites are incredibly rich in elements from the 6 metals of the platinum group, about 10,000 times more abundant than in the Earth's crust. And this amount of PGM present in a given sedimentation layer could be very precisely measured. Luis decided that iridium, not platinum itself, was the best element to measure because it was the most easily detected. Luis also knew just the right people to do the measurements. Nucleus chemists Frank Asaro and Helen Michael at the Berkeley Radiation Laboratory. Walter provided Asaro with a set of samples from across the Gubbio KT boundary. Then began the long wait for results. Months passed. The analytical techniques were slow, needed equipment which required routine maintenance and calibration, and Asaro had other projects to juggle as well. Finally, 9 months later, Walter got the call they'd been waiting for. Asaro and Michael were ready to share the results. What they found was astounding. They expected to find iridium levels of around 1/10 part per billion. Instead, the clay layer contained 3 parts per billion. 30 times more than the investigators expected. The team was electrified. This wasn't just a geological curiosity. The team had discovered a cosmic calling card. The immediate question to Walter was then, is this iridium anomaly unique to Gubbio? Or could this clay layer define a broader occurrence, possibly even an Earth-wide cosmic event? Walter set out to find other exposed KT boundary sites. He first traveled to Denmark, while colleagues checked sites in Spain and New Zealand. The results were consistent. Everywhere they were able to find the clay sedimentation layer, they noted a similar spike in iridium levels to that discovered at the first site in Gubbio. It became clear that this clay layer in other locations was devoid of fossils, as was Walter's initial discovery. It was worldwide and defined the KT or KP boundary as a worldwide extinction event. The evidence was pointing to something both massive and global. But what could cause such a worldwide phenomenon? The team considered several possibilities. Could Earth have passed through a cloud of iridium-rich interstellar dust? Might the sun have become a nova? Perhaps the iridium came from some other planet somehow. One by one, these ideas were discarded. They didn't fit the evidence or were physically impossible to have occurred and Earth to exist as it does today. Then came the breakthrough. What if a huge asteroid had struck the Earth? Lewis crunched the numbers based on the amount of iridium in the clay, which he now knew encircled the Earth, and the size of the planet. He calculated that the asteroid would have been about 10 kilometers in diameter, or a bit more than 6 miles. The impact of such an object on Earth would have been catastrophic. Entering the atmosphere at over 50,000 miles per hour, an asteroid of this size would have punched a hole in the air even larger than 10 kilometers. The energy released at impact would have been equivalent to 100 million megatons of TNT, millions and millions of times more powerful than the largest nuclear bomb ever detonated. For comparison, the largest atomic bomb of World War II was a .021 megaton bomb of about 21 kilotons. The immediate effects would have been apocalyptic. The asteroid and a very large area surrounding the impact site would have vaporized instantly. A tremendous fireball would have erupted into space, and shock waves would have spread down into the bedrock, and then curved back into Earth's atmosphere and launched countless tons of molten rock high into the atmosphere. This is what occurs during a large volcano eruption, but massively larger. And the devastation wouldn't be limited to the impact site. Ejected material would rain back down across the planet, heating the atmosphere and igniting global wildfires. Tsunamis would race across oceans, and earthquakes would shake the entire planet. In the following months, and probably for several years, dust and soot in the atmosphere would block out the sun, plunging the Earth into a dark, impact-caused extended winter. Photosynthesis would shut down, collapsing food chains from the bottom up. The results were catastrophic for Earth. More than half of all plant species disappeared in some locations. On land, no animal larger than 25 kilograms, or about 50 pounds, survived. The skies emptied of pterosaurs, the seas of mosasaurs and plesiosaurs, and yes, the dinosaurs, which had dominated terrestrial ecosystems for over 180 million years, died. In 1980, the Alvarez team published their asteroid impact hypothesis in the journal Science. It was a bold claim, synthesizing evidence from geology, physics, and paleontology. It was earth-shaking. As with many new discoveries and new hypotheses, not everyone was convinced. For over 150 years, geologists had taught and been taught that there had been gradual change in Earth's history. The idea of a sudden catastrophic event seemed almost heretical to some. Some paleontologists pointed out that the highest dinosaur fossils were found 3 meters below the KT boundary. Could the dinosaurs have already been extinct when the asteroid hit? And there was another problem. Where was the crater? If the asteroid had struck an ocean, which covers more than 2/3 of the Earth's surface, could it be found? In the next decade, scientists scoured the Earth for clues. They examined rock formations, studied microfossils, and mapped the ocean floor. The breakthrough came from an unlikely place. The sandy bed of the Brazos River in Texas. Geologists found evidence of an enormous tsunami, perhaps more than 100 meters high, that's 300 feet, which occurred consistent with the timing of the formation of the identified clay layer, the KT boundary. Then glassy rocks called tektites were discovered in Haiti. These were pieces of earth rock that had been ejected by the impact, melted, and rained back down. These clues pointed to an impact somewhere around the Gulf of Mexico or the Caribbean. In 1991, the smoking gun was finally revealed. A team of scientists identified a 180-kilometer wide crater buried beneath the Yucatan Peninsula in Mexico. Named the Chicxulub after a nearby village, the crater was exactly the size predicted by the Alvarez team over a decade earlier. Subsequent dating of the impact melt rock confirmed its age, 66 million years old, precisely consistent with the time estimated for the KT boundary. As more evidence accumulated, the impact theory gained widespread acceptance. Today, we can trace ejected material from the Chicxulub impact at over 100 sites around the world. But the story doesn't end there. Recent evidence suggests that the Chicxulub impact may have triggered massive volcano eruptions in India, known as the Deccan Traps. These eruptions had begun before the impact, but intensified dramatically afterwards. This has led some scientists to propose a 1-2 punch hypothesis. The asteroid impact was the first blow affecting the Earth's tectonic plate structure. The subsequent volcanic activity, spewing enormous amounts of gases into the atmosphere, may have been the knockout punch, prolonging and intensifying the global die-off of both animal and plant species. While the KT extinction was a catastrophe for both animal and plant species, it also created opportunities. The disappearance of the dinosaurs allowed mammals, which had been small and mostly nocturnal, to diversify and evolve into new niches. Discovery of this important event began when a curious geologist was studying a thin layer of clay in Italy. His tenacity and perseverance resulted in discovery and understanding of the KT extinction. His work also reminds us that Earth's history is not always one of gradual change. In the 66 billion years since the impact, life has rebounded in incredible ways. New species evolved to fill the roles left vacant by the species lost as a result of the extinction event. This period of recovery and evolution eventually led to the emergence of our own species. Sometimes Earth-born and cosmic events rewrite the rules of life itself. Today, we're more aware than ever of the potential for cosmic impacts. NASA and other space agencies track near-Earth objects, and scientists are developing strategies to deflect future potentially hazardous asteroids. And we're reminded of life's resilience. Despite total annihilation of multiple species, plant and animal, life on Earth rebounded. It also diversified and thrived. The results following the KT event are a powerful testament to the tenacity of life and the ever-changing nature of our planet. As we peer into the cosmos, we're reminded that our planet's history, and perhaps its future, is intimately connected to the story of the stars. The same processes that brought destruction 66 million years ago also delivered the building blocks of life to our young planet billions of years earlier. This cosmic connection isn't just ancient history. It's our present now and will be in our future. Today, as you watch this video, astronomers are scanning the skies for potential asteroid threats, while scientists develop strategies to protect our planet. We are the first generation of humans with the knowledge and capability to potentially prevent a future asteroid-driven extinction event. The story of the KT extinction reminds us of three profound truths. 1. Life is resilient. Despite total annihilation, it rebounded and thrived. 2. Change is constant. The fall of the dinosaurs paved the way for the rise of mammals and eventually us. And 3. Knowledge is power. Understanding our past helps us shape our future. So, the next time you look up at the stars, remember you're not just gazing at distant suns. You're looking at the cosmic forces that shaped our past and will influence our future. In the grand story of life on Earth, we're not just observers, we're participants. The dinosaurs couldn't stop their extinction. But armed with science and determination, perhaps we can alter what might have been a future impact from a massive asteroid. If you enjoyed this journey through time and space, don't forget to like, subscribe, and share. And remember, every rock, every fossil, every star in the sky tells a chapter in our universe's incredible story. Keep exploring, keep questioning, and keep looking up. The greatest discoveries may yet lie ahead.